job is to find the largest just in this portion of the array. And this is an interesting subproblem that people have to solve in larger problems. We won't go there, but our job is to answer these queries as quickly as possible. And typically, the array can be thought of as large, but really the number of queries are very, very large. They're like infinite. They may be happening every day. And so there's no limit to the number of queries we are asking. So what we really want to do is to speed up the cost of each query. And each query simply says, oh yeah, that array that you had, just find me the largest in the range I through j. You don't have to look at the whole array, you just have to look at this small portion. And again, there's a naive solution for this where all you do is start at location I, walk your way down through j, and find the largest item in that set. And so this is going to still be big O of n per query because you have no idea where I and j are. I could be 1 and j could be somewhere near the end, and so it's possible that you have to look through the whole array. So in the worst case, the naive solution is simply going to be big O of n. So if there are lots of queries where I is somewhere near the beginning and j is somewhere towards the end, then the cost of queries becomes way too much. And so this is what you want to try and speed up. And so we talked about how one could do this given the fact that the array that we have to query is fixed. It's given to you well in advance, and you can do whatever you want with it, and you can pre-process it so that you can answer these queries as quickly as possible. Now, we looked at several versions, and the first version that we came up with took this array that we have. In this case, I've shown you an example, and we created what's called as a two-dimensional array. This two-dimensional array essentially has all the possible answers. So if you want to go from 3 through 7, then you can go over here. 3, 7 will tell you what the answer is. So it tells you that 29 is the largest value between 3 and 7. Okay, so essentially the answers are all they're all pre-computed, stored in an array, and all you do is go and pick out whatever answer you want depending on the query. So it doesn't matter how many queries you have, all it takes is a quick lookup. And that lookup essentially takes constant time. So now by pre-computing, by pre-processing this array in this simple way, we figured out how to answer the query very, very fast. But the downside is that now we have to store this big two-dimensional array and look it up anytime we want. So the space complexity becomes too high, but the time complexity per query becomes very, very small. So these are your two possible quick solutions. We should be talking a little bit about pre-processing, and it turns out that in order to pre-process, remember we have to create this two-dimensional array, right? And that two-dimensional array can be quite expensive to compute. In fact, if you don't do this smartly, each of these computations could take you big O of n time, and because there are 2 for loops in order to compute the whole two-dimensional array, this whole thing could end up being big O of n cubed. And so slowly you see that your space is very high, your pre-processing time is too high, and the whole thing is just blowing out of proportion. It's getting very, very expensive. Now, here the good thing, of course, is that the queries are super, super fast. In fact, you can solve that in constant time. So if you have k queries, it only takes you big O of k plus n cubed, where k is, remember, since each query takes you only constant time, k queries can be answered in time k, and this is the cost of the pre-processing, right? So building the array. So the total cost can be written down in this manner, and what we're really, really trying to do is to make this fast without this being as expensive as this. We'd like to see if there's some middle ground that we could come up with where we could lower the pre-processing time and space and see if we can still do the queries super fast. So there is one simple way to improve. It turns out that filling the array, the two-dimensional array that I showed you, can be done in a smarter way. And if you do this, you can fill up each entry in roughly constant time. And if you do that, it actually speeds up the pre-processing time quite a bit, brings it down from n cubed to n squared, and still keeps your query cost to be very small. Okay. Any questions before I show other things? Okay, so far so good. So really what we have is summarized in this picture. This says if I want to find the maximum, if it's just a basic version, then all I have to do is to look through the whole array. I can do that in big O of n time. And it's very simple. It's almost naive, but it's optimal. It's the best you can do. If you want the query version, if you don't want to spend any pre-processing time, this becomes essentially constant or 0, but every query becomes quite expensive. It becomes big O of n, right? So therefore, the total cost of k queries is k times n, assuming that you do no pre-processing. Now, we also saw this version where we said, let's create a two-dimensional array, but if you want to do it that way, the pre-processing time and the pre-processing space is n squared, but your query time is now all the way down to a constant, right? And so the cost of k queries is now becoming k plus n squared. So all this sounds good. What we want to do is to come up with a third method, and this is what we discussed in the last class. We saw that there is a tree-based approach, which is a nice compromise between these two crazy methods. Okay. All right, so let's talk about that. In the tree version, what we said was something interesting. We said, let's say you're given an array. I should show the array first. Where is the array? There's the array. If this is the array, and if I'm allowed to pre-process this, what I'm going to do, remember, I'll be given this array to pre-process, and then I'll be given queries where I'll be given some range, and I'll be asked, tell me the largest item in this range, or whatever, right? Now, in order to pre-process this, instead of storing things in a large two-dimensional array, I'm going to store this in a tree. And in order to store this in a tree, let me first figure out what the indices are for each of the entries. And then I'm going to create this particular tree where what you'll see is that the array entries go down at the bottom of the tree. They become the leaves of the tree. And then I have a binary tree where things are paired up and merged at the next level. But as you merge them, you'll see that I am noting down the larger of the two values that are in the leaves at the underneath that node. So here, 21 is the largest, here 6 is the largest, here 14 is the largest, here 7 is the largest. And then when I go one level up, I do the same thing. I take the larger of these two and store it here, which is equivalent to saying this is the largest in all 4 of these items, right? And then this is the largest in all, in this case, 3 of these items. The 4th one is a blank. And then this here tells you what's the largest in this entire tree, right? So I am now storing things in a very different way. Instead of a two-dimensional matrix, I'm storing it in a tree. Now there are a bunch of useful, interesting features of this tree, and let me let me recap some of the ideas that are captured by this tree. What I said last time was that the first idea is to organize this as a balanced binary tree. And the good thing with this is that the height of the binary tree is going to be only log of n instead of n, right? Because it's log n, you'll see later on that it has lots of good implications. Then the idea number 2 that we used here was that the leaves of the tree actually stored all the items, okay? So that so the rest of the tree essentially has partial information of the things that we've looked at. And so the internal nodes of this tree contains answers to queries for some of these ranges. So if you ever ask me a question for the range 1 through 2, I can quickly answer this without having to actually go and process this. Or if you ask me for 1 through 4, I can answer this without actually processing all of this part of the tree. All I have to do is to get here, and I'll tell you that between 1 and 4, the largest item is number 21. Okay? So I've stored some information, but I don't have every possible query stored in this tree. However, I have sufficient information here that I can still answer lots of queries pretty quickly. And then the fourth idea is that, I already mentioned this, every node has the information on the largest item in that entire subtree that's underneath it, right? There's one other little point that I want to make. This here is what is also called as a binary search tree. And some of you may have seen this in your data structures class or somewhere else. They were called as red-black trees or 2-3 trees or something else. So this is actually an example of a binary search tree, but there's a fundamental difference. In a binary search tree, you organize things based on what is larger and what is smaller, right? You put small things on the left side, you put large things on the right side. That's not what you're doing here, because the original array just goes in on the leaves from left to right. You never sorted it, you never said, oh, this is a large guy, I'm gonna put it at the right side. But I'm still saying that this is a binary search tree because this is sorted based on the array indices, not on the array values. Okay, so for instance, over here, if you look over here, you'll see that array indices 1 through 4 are on the left side, array indices 5 through 7 are on the right side. So based on the index, the position or the location where that item is, that's what we are using to put them either on the left side or the right side. Okay. Now that's a minor difference. So it's not a true binary search tree in the original sense of the term, but it turns out to be valuable enough that you can use a lot of the principles that you used for binary search trees in order to do some search. And that's what I'm going to quickly recap. We did this last time, but I'm going to recap because there are some new people here. In fact, if you look at any specific node in the tree, you'll see that every node has a range. If this range is A through A to B, then the node on the left side will go from A to somewhere in between A and B. In fact, it'll go to the midpoint of A and B, right? And this guy here will go from the midpoint all the way to B. So the left piece will go here, the right piece will go here. If the value stored here is P and the value stored here is Q, the value that will be stored here is whichever is larger, right? And that's the way you organize things. This is a snapshot of what happens at any node in the tree, but the entire tree is organized on this exact same principle. Okay? So if you understand this, you understand pretty much the whole picture, and all you need to know is figure out where the midpoint is. And so that tells you what the index is, and it'll tell you which way to go, left or right. Okay? Now we did talk about how we answer a query, because that's the hard part. Eventually you're going to be asked a query, and your goal is to figure out how to answer this query. I'm going to skip this slide. We went through it last time. I want to focus on this picture here. So let's assume that we have this tree that I showed you, right? The tree, remember, is organized in such a way that at the leaves you have all the items in the array, and then you've broken it down on the left side, right side based on array indices. So lower indices are on the left and the larger indices are on the right. Now, if I want to search for the range 5, 6 in this tree, what would I do? Well, I always start at the root of the tree. And then based on which way the numbers go, I'll either go to the right or to the left. And in fact, for 5, 6, I'm going to start at the root of the tree. Remember, I'm not drawing the whole tree here. In fact, the whole subtree below 1, 4, I haven't even drawn it. Why? because I'm going to start at 1, 7. Because I'm looking for 5, 6, I'm going to go over to the right. And when I go to 5, 7, it'll tell me that 5, 6 should be in the left subtree, and I go down there and I find it there and I can stop. So essentially, what happens is that all the nodes that are shaded this slightly, whatever this color is, orangish, yellow, those are the nodes that I actually visit. The other nodes, I don't even look at them so this becomes what's called as the search path in the tree for the range that I'm searching. So if I'm searching for 5, 6, this is the path I'm going to look for it. And then what you'll see is something interesting. You'll see that all those subtrees that I've either crossed out with red or green, those are parts I'm not even going to bother looking at, because those parts, those ranges are outside of 5, 6, right? I'm interested in figuring out what's the largest in this range, 5, 6. So why should I look at 1, 4? Why should I look at 6, 7? And so on and so forth. So those are all parts that I'll simply ignore. And so the only parts that I look at is what is called a search path in the tree. If you think about it, that search path will start at the root, will either go left or right. These are the only choices it will have. So a typical search path will look something like this. All right? Now, as you traverse this path, and as you look for your item, what you'll see is that you will bypass some subtrees and decide that those are not worth looking at because they're outside your range. Okay? Then these are things that you would do when you're going to the right. At the same time, if you're going to the left, if you make a left turn, there will be subtrees on the right that you're going to ignore. And those are things that are not relevant because they're outside your range. So you start here, look for your range. It'll tell you to go left. Then, oh, I forgot to draw another tree over here, sorry. So I will ignore a green subtree here. Then I'll come here, ignore this red subtree, ignore this guy, and so on. So because my path tells me how to find the interval that I'm interested in. Yeah?
What if we're given a range like 4, 5?
Yeah, I'll get there. Good question, but give me just a couple of minutes, yeah? That's right. So there are more complicated ones, but this is a simpler range. And what it tells you is how this search will happen, right? Now, oh yeah, I also forgot to add 2 more subtrees for this bottom node here. But there are a bunch of things that you're just ignoring. Now, what you'll see is that all the green, why are some of them in green and why are some in red? Anyone know?
Are green the ones that are part of the range?
Actually, all of them, all these were things that were ignored, so they were outside the range. So why are some in green and why are some in red?
Do they contribute to the max value?
Well, because they're being ignored, they actually don't, right? Look over here. I'm interested in 5, 6, so I can't report this 21 because that's the range 1 through 7. I know I don't have to look at 1, 4 because it's outside my range.
Well, that's all the red subtrees in the.
That's right.
Yeah.
So anytime I go right, I'm going to ignore a subtree on the left. I'm going to color it red, just so that it becomes clear. Anytime I go left, I'm ignoring a subtree on the right. I'll just color it green so that you understand this. Now, a better way to understand this is that the red subtrees correspond to ranges that are to the left of the range you're searching. Okay, whereas the green subtrees correspond to ranges that are larger than what you're looking for. Okay, so for instance here, the one I crossed out, I know you can't read it, but it said 1, 4. And remember, you're searching for 5, 6. So 1, 4 is out of the range, but it's to the left. This guy here was 6, 7. Again, it's a range outside your 5, 6 search, but it's to the right. This guy here is is, I think it's 5, 5, so it's over to the left. And this guy here is 6, 6, which is over to the right. Okay? All right, great. So as you do this search, there are things that fall to the right and things that fall to the left that you could ignore. And if you actually find the range at the end of this search, then you can just report it. Okay? Now we get to your question, which is what happens if you're given a range like 4, 6, that's not in the original tree. Okay? If I'm given 4, 6, then what I do is the following. I first locate 4 in the tree, then I locate 6 in the tree, and then I have to look for things in between. So if I look for 4, it'll take me somewhere, okay? And I would have looked at a bunch of things along the way. I know that 4, 6 is not in the tree, but I can locate 4. Once I locate 4, I know all the things that are above it. So I know those are subtrees that are going to be still in play, right? Because they're all larger than 4, and I want to get from 4 to 6. Then I will look for 6, which will be another path where there'll be a bunch of red subtrees on the left and green subtrees on the right that you've ignored. But the red subtrees are smaller than 6, and the green subtrees are larger than 6. So therefore, I'm going to pick up all the green subtrees on this side, all the red subtrees on the right side, when I'm looking for 6. Those will help me give me the answer for which is the largest. Does that make sense? So even if a range is not there, all I have to do is take the range, isolate the left side, isolate the right side, locate it in the tree, and look at all the subtrees that fall in between. Okay, so I will be looking for a path that comes like that, and all the subtrees in between, those are between 4 and 6, right? Between I and j. And those are the ones that will contribute. Now the good thing is that for each of the subtrees that are still in play, I don't have to go and visit the entire subtree, because the largest value is stored right here, right? Because for every subtree, I have the largest value already computed and stored. So in order to find the largest value, I just look at this, and then I will go on the right side, and I'll have a bunch of subtrees there. I'll pick up all those largest values and report the best that I've seen so far. Now, the question is, how much work was all of this? And that's where the real hard problem is. Is everyone okay so far? Are you with me so far? Yeah? Okay, so the good thing is that the search path always starts at the root of the tree and goes down, okay? Because every time I make a comparison, it tells me whether to go left or right. If I'm searching for 4, I know exactly whether to go right or left. So I'm going to go right or left, and I'll get to 4, and I will know exactly which subtrees I haven't looked at, but are still in play. So these subtrees, the ones on the right, the ones that are larger than 4, they are still in play. I'm still interested in them, but I haven't looked at them. Okay. Whereas for the 6, there are a bunch of subtrees to its left that I haven't looked at and that I need to look at. Now, how many subtrees do I need to look at? It's essentially the length of the search path, which is the height of the tree. And the height of the tree in this case is log of n. Okay? And therefore, I have log n subtrees here, log n subtrees here. All I have to do is to pick out the largest that is stored in the roots of each of these subtrees, and I'm done. That's my answer. Is that clear? So a little bit complicated, but that's how it goes. If you want, we could go through an example here. Yeah, let's do an example here. let's say we want to go from 2 to 6. Okay, so I am going to turn this off and see if I can write on it. Okay. Okay, good. So what? Okay, that's fine. So let's say I want to find the largest value in 2, 6. Okay. So the way I described to you, I am going to first locate 2 in the tree, then I'm going to locate 6 in the tree, and then figure out the answer. Now let's locate 2 in the tree. I will always start at the root. So I start here at the root of the tree. Now the range is 1, 7, and the left subtree has 1 through 4, right subtree has 5 through 7. So therefore, since I'm looking for 2, I know I have to go to the left subtree. Is that clear? Everyone okay with this? Remember, I'm looking for 2 now, okay? And it says go to the left. Okay? Which means whatever is on the right side, I'm going to ignore it for now. I go to 1, 4, and then it says 1 to 2 is to the left, 3 to 4 is on the right. So therefore, since I'm looking for 2, I again go to the left. Is that clear? So from here, I go again a left. So I'm here now, and then this side says it's just 1 to 1, and this side says it's 2 to 2, so therefore I'm going to the right. So this is my search path for just 2. And since I went left, I'm ignoring things on the right side. Let me see if I can do some picturization here. So remember, I'm going to ignore this subtree here, and I am going to, well, there is nothing below this, so I don't have to worry about it. So essentially, that's one subtree that I've ignored. There's also a subtree here, but that comes into play. You'll see that becomes relevant. And then I also have a subtree here that I ignored. Oh, I should have made this green and this red. I'm sorry. Okay. All right. Once again. So we're on green. This is green. So here's the subtree that I've ignored, and here's the subtree that I've ignored. Is that clear so far? Yeah. Now I'm going to go and search for 6, and when I search for 6, this is what it looks like. Again, I start at the root of the tree. 6 would be found on the other side, right? So I go there, and then 5 and 6 are on the left side, so I go left, and then 6 is on the right side. Are you with me? Okay, so I come down here, and here, which are the subtrees that I've essentially ignored? And you can figure this out. You'll see that I've ignored a subtree over here, and I've ignored a subtree over here. Okay? Now, in order to figure out the largest in 2, 6, okay, here's what I have to do. I have to find the green subtrees here and the red subtrees here. Remember, the green subtrees are larger than 2. The red subtrees here are less than 6. I want to take all those subtrees between 2 and 6, find the largest and report it. Okay, so this one is not quite relevant. We'll ignore that for a second. We have to find the largest on the right side here, and the largest here on the right side would be 6, right? So this number is going to be 6 from here. And then I go down here, and eventually I'll come down here, and the largest that I see here is going to be 9. Okay? This guy I don't have to worry because it's outside my range. So this 9 is important, this 6 is important. Then when I come down here, this green guy I don't have to worry about because that's outside my range. And this red guy will give me 14. So this one will give me 14 because it's in my range. And then when I go down here, it's going to give me 11, but that's not relevant also. So I'm going to find the largest of 9, 6, 14, and 11 and report that it's 14. Okay. Now what did I save in the process? What I saved was searching through these subtrees. There's a large subtree there, potentially large subtree, that I didn't go and actually search because they were pre-computed. All right. So for each level in the tree, I only looked at one value on the left side and one value on the right side. So the total cost, the total number of comparisons I make is roughly 2 times the height of the tree, which is 2 times log n. Is this clear? So that's how finding the maximum in any range that you like, I can do it in 2 log n time. So any range you give me, if you give me I comma j, I'm first going to locate I, I'm going to then locate j, I'm going to find all the subtrees that are hanging off on this side of I, I'll find all the subtrees that are hanging off on this side of j, and I'll just find the largest among each of these subtrees. Clear?
If I may ask, what's the time complexity of building the tree?
Very good question. Yeah, so we do have to worry about this. Remember, this tree has to be ready in order to answer all those fancy questions, right? So we have to worry about that. Before I answer this, let me make sure that, is there anyone who has answered the questions about this claim that I have, that search, once the tree is ready, I can search in 2 log n time. You believe this? Are you okay with it? Any questions? Because in each case, you walk down the tree, the height of the tree is log n, I find the path, I find all the trees that are hanging off, and for each tree, I just go and pick out the largest, which is already stored at the top of that tree. Right? Done? Okay, so next let's look at Jocelyn's question. How do I build this tree? This looks ugly and big and lots of complicated stuff. What do I do? Well, it turns out to be reasonably simple. You know that the leaves of the tree has the original array items. Of course, I may have to pad up a little bit extra here at the end. I won't worry about it now. And then I build the next level of the tree by simply taking them in pairs, right? So I just pair the first 2, then 3 and 4, then 5 and 6, and then 7 and 8, and then I pair them up and I get the next level. Again, I start with the next level, treating it almost like the bottom level, and again I pair them up and build the next layer. I keep doing this. If necessary, I'll put in some extra null nodes in order to pad things up, and in the end, I will just get one binary tree because the whole thing has to collapse. Right? Now, how quickly can I do this? Do we even know how to do this? Can you write code to build this tree? What do you think? So first, your job is to build the tree, then you have to put in appropriate information there. So these are 2 different tasks, and we can first consider the question of how do I build a tree that has n leaves. Okay? And you do exactly the way I just said. You put 1 and 2 in the bottom, and then build a parent for them. Then you take 3 and 4 and build a parent for them, and you keep doing this. Then you start at the next level, take the first 2, join them by a parent, and build the level above. And you keep doing this until you have only two nodes at the last level, and you build the root of the tree. Okay. Writing code for this is a bit non-trivial, but I encourage you to try this out, and I'm happy to discuss this next time if once you've given it a try. I don't want to just tell you how this works. Yeah. Any other questions? So the way I've just described it, you're just pairing them up and creating a new node and just joining them. So how much time do you think it'll take?
N log n.
Sorry?
N log n.
N log n, the reason is what?
I think because you have to go through the array and then each one you start making more pairs and then there's
Right.
less.
So at the bottom level you have n nodes and you have log n levels. So n log n sounds like a reasonable guess. Is there anybody who has a better guess or a different guess? Well, in order to get an improved guess, what you need to do is to figure out how many times you have to do this operation of taking two nodes and building a parent node. Now, you started at the bottom with n nodes, roughly. The next level had only n over 2 nodes, right? For sure. Yeah? Then we had n over 4, n over 8, and so on and so forth. So each time, at each level, you were doing half the work in order to build the next level. Correct? So therefore, the total amount of work is, sorry? It's O of n because of the same argument we had last time. If you do n plus n over 2 plus n over 4 plus n over 8 plus n over 16, all the way up until it collapses, this is what's called as a geometric series. And because the ratio is a half, you'll see that it collapses pretty quickly. And the right answer is 2n. When you add up all of this, that sum is less than 2n. Okay? And therefore, the total amount of time it takes to build the tree is roughly 2n such node creations. 2n times I have to take pairs of nodes and create a parent node and connect it. And if I do this 2n times, sorry, if I do this n times, I'm actually done. Is this clear? Okay, so now we can summarize everything we've learned. Here's a summary of what we learned. We talked about the basic version, the first query version, and the simple query version, and the fancy query version where we had a two-dimensional array, and now we have a tree version. The tree version, the tree can be built in big O of n times, so that's pre-processing time. The amount of space is also big O of n because the number of nodes is, again, at most 2n. And so therefore, the cost of each query, oh, I made a mistake, I'm so sorry. I just see it. What's wrong here in the query time? Well, I did write log of n, but I put the total time to be incorrect. That was incorrectly put in here. This should be
N log n.
K log n?
n log n is already here.
2 log n.
N cross n log n.
What am I missing?
The login should be multiplied by k.
That's right. Remember, there are k queries. Each one takes log n time, so this should be k log n plus n log n. N log n is the cost of, I don't need n. This is actually just n. So yeah, there are two mistakes here. I need to fix both of them. So this should be k log n plus n. Remember, the tree can be built in n time, then each time I answer the query, it takes log n time. Since there are k queries, it's k times log n, right? Clear? Okay, I'll fix that before I post it. Any questions about this? Modulo the corrections there. Fine, can we move on? Okay. So anyway, this tried to answer the question. So by the way, how is this a compromise between this version and this version? what you'll see here is that the pre-processing time was very low in the first version and very high in the second version. Here it's somewhere in between, right? You saw that the query version had, this query version had a very expensive query time. This one had a very low query time. This one is somewhere in between. Okay? And then when you look at the total cost, what you'll see is that it's actually it may be better than both of these depending on how big K is. Okay? If K is very, very large, most likely this will be better than both of these. Okay? So what you need to, the takeaway from this is that which version is better is not something that's established right at the start. It depends on your application. You have to figure out how big your N and K are and then make that decision. Is that clear? Okay, so let me move on to a new problem, finally. So all of this is actually a recap of what we did last time. Sorry about that. Let's talk about a new problem. In this new problem,
Quick question.
yeah.
For the competitions, how are they judging, like the scoring? So like on
yeah.
on
Yeah,
the
they're not
code
going
stuff,
to
it
check
kind of
your,
boils down to.
so they're not going to check your time complexity. No one's going to ask you questions about the time complexity. So how do they check? Well, they'll give you a data set that's large enough that it'll mess you up.
Oh. Okay, cool.
Yeah. So if they want you not to get an n squared solution, okay, all they have to do is make K and N to be equal and large.
Yeah.
Okay,
So
so
they
let's
judge
say they
it.
take N equals 1,000,000 and K equals 1,000,000. So if you use this, it's going to be 1,000,000 times 1,000,000, which is 1,000,000,000,000, and you can forget it. You're not going to get it done in 1 second, right? If N is 1,000,000, N squared again is 1,000,000,000. You're dead in the water. So the only way out is getting K times log N plus N, which will be log of 1,000,000 turns out to be about how much? Log of 1,000,000. Log of 1,000 is how much?
10.
Yeah. What is log of 1,000 roughly?
10.
So it's about a 10 because 2 to the 10 is 1,024, right? So log of 1,024 is about 10. So let's just say for 1,000 the log is 10. For 1,000,000 it's going to be 20 because it's a square of 1,000, right? This is how logs work. When you square it, the log of a square is 2 times the log, right? Remember this from your discrete math days when they tortured you, left scars on you, I think. So log of 1,000,000 is somewhere in the range of 20. Log of 1,000,000,000 is somewhere in the range of 30. Okay, so for every 1,000 you add another 10. Got it?
Yeah.
Keep that in your head. It's very easy. 1,000 is roughly a 10. Okay? So for every 1,000 that you multiply, you add another 10 to it. So therefore, if you're doing K log N plus N, the total cost is going to be 1,000,000 times 20 plus another 1,000,000. So you get something like 20 to 21 million, which is doable. Is that clear?
Yeah. So ultimately, it's they judge on pass or fail.
If there are 2 ways your program can fail. One is if it just doesn't work and gives you the wrong answer, then you're dead in the water. Or if it takes too long. So they have a timeout option. They'll tell you your thing has to run in under 1 second or something like that. And if in 1 second it doesn't give you, if their tester doesn't get an answer, it'll say timeout. So then it'll just reject it because it could be an infinite loop, it could be some other silly thing you've done, who knows what, so they just time it out. Yeah.
Does the language you use, can that influence?
It can influence, yes, that's a good question. Some languages, the native compilers and the native processors end up going a little slower. Python is just a tiny bit slower than C++. Java also is Java is probably somewhere in between C++ and Python, so it could make a difference. But then, for most part, they set a time limit in such a way that the language doesn't matter. They write code in all the languages that are relevant for the competition, test it out, and make sure that all three run. That's how they set the time. But they do know how they do look at the non-optimal versions of the algorithm and make sure that you don't slip into that, typically. Now, there are going to be cases where they will allow you to write not so optimal algorithms, and in such cases you get clues from the values that they use. So if n is not 1,000,000, if n is something like 20, then you should know that n squared, maybe even n cubed is okay, right? And so you figure out based on the information they give you. Those will give you clues as to how efficient your algorithm needs to be. If the numbers are small, there's a good chance that just try something brute force and get it to work. If the numbers are large, it's there for a very good reason. It's probably because they don't want you to come up with the naive brute force solution, okay? And in some sense, this here is the brute force solution, because you're not thinking about anything. If the question is, give me the largest between I and j, brute force, start at I, end at j, figure it out, yeah?
And something else I'd like to add
Sure.
to that is, like Giri said, they will give you the constraints. And they're not doing that just for fun. So like if you see n less than or equal to 100,000, like there's definitely
a reason
data,
for it, yeah.
There's test data that goes
And
up
for
to
sure,
100,000.
they'll set up test data in order to test you, because they want to make sure that you're not writing brute force code. Okay, so competitions are there for two reasons, both to make sure your algorithms are correct and that your algorithms are efficient. I said that on the first day. Those are two things you have to worry about with these competitions. But that's what makes it fun. Otherwise, brute force, almost anyone may be able to write it, and then just life gets to be too easy. Other questions? Okay, excellent. So, new problem. Here, the problem is that you're asked to search an array, but this is an array that's already sorted, and it may have lots of repeats. So here's an example. I have 1, 1, 3, 3, 3, 3, 6, 9, 9, 9, 15, 24, 24, 24, 39. You see that it's sorted. It never decreases, it only increases or stays the same. But the only problem is there could be repeats, okay? So now I have a simple question to ask you. You need to find what's called as the mode. If you've taken a statistics class, you know that the mode is the most frequent item, right? So if I give you this array, what's the most frequent item?
3.
It's 3, right? Easy to see. All you have to do is to go left to right, and it's always increasing, and you keep track of the count, and whichever is the largest count, you should be done. Yeah, the for loop is a little messier, but you can do it, right? Okay, so this is an easy one, and what's the time complexity? It's still O of n, because all you're doing is now you're just keeping track of the item with the highest frequency, right? Great, so this can be easily done with a little fancy for loop, but nothing too fancy. This is something you might expect in your first programming class, perhaps, right? Great, now I want to change the problem, make it a little harder, right? And similar to the ones that we've been looking at so far, let's do find mode. Remember, mode means the most frequent item, but now I give you a range. Okay, I tell you that I want you to tell me the most frequent item in locations I through j. Very similar to what we did before, right? Except that now we have this range going on. All right? So again, brute force is quite easy, right? Because if I want from I through j, I start at I keep track of the frequency of each item. I only have to keep track of the frequency of the most frequent item that I've seen so far and see if it gets beat, right? So I can do this in time that's as much as the size as the size of this range. And since the range can be very, very large, this could still take big O of n time per query. Is this clear? So it's all looking very similar to our previous problem, right? It should remind you of that. So therefore, if I don't do any pre-processing, I can solve this in big O of n time. It's very clear. Now, we did this, the query version of the previous problem where we did some fancy work, but we reduced the query time to a constant. Can we do that here? Remember, what was our approach? Our approach was to build the 2D array, right? Remember this?
Yeah.
So can I do some trick like that to reduce the query down to a constant? Yes? No? You don't think so? Easy? Is this easy? Sort of easy? It's not trivial, but it's not hard, right? For every possible range, I through j, I could go and figure out what's the most frequent item, put it in an array, and I'm done, right? Getting this pre-processing to be down to n squared takes a little bit more work, but we can figure this out. It's not undoable, right? Is that clear? I'm seeing some blank faces, so you better ask questions, otherwise I just keep going on as if everything is fine. All okay? All okay. Yeah, the others will need to ask, otherwise I will be like a freight train, I'll just keep going. All right? So it turns out that, just like before, I could come up with a slightly improved version where I spend a heck of a lot of time and a heck of a lot of space, store the answer for every possible query, I store it in an array, two-dimensional array, and I can answer that in constant time. Okay. So the real question is there a middle version? Yeah?
There's space
I'd
for
say
it
yes.
inside.
You say yes because I'm leaving space there. Maybe, yeah. Is it coming? Is it clear in your head how you would approach this? What should I be doing? Any thoughts?
A tree.
A tree? Yeah. Great. In fact, that's what I want to ask you. If a tree-based solution would work here, and you think yes. Okay. Anyone else thinks this would work? A tree-based solution like last time? You're okay with that? You think it'll work? Is it somewhat clear in your head what the tree looks like?
I think similarly to the last problem, we could sort of set like sub-ranges and keep track of the most frequent value in those.
So what do the leaves of your tree look like? Are they the original array, or what is it? Is it something else? And what are you storing in each node? Are you clear about that? Because it's not the maximum anymore.
The
Right.
frequency of the most
Frequency.
like, or the most repeated. How many times the value is repeated? So like if we have 111.
Yeah. Remember when you merge to let me go back to that earlier picture that I had. Remember this picture? Any node anywhere in this tree looks like this. Okay, this range gets split up into two, and these two maximum get updated at the parent by the larger of the two, right? This was how we stored that tree. Is that correct? Now my question is, what is the equivalent of this for our find mode problem? Are you clear about that? Can you draw that over here? Let me erase this. Do you think we could draw the equivalent of this on for the find mode problem? Is it very clear? Remember, there are some tricky things here. The tricky things happen because of what?
So we could have a number from the left side that's also on the right side.
Yeah, that's the annoying thing. That's right. Because there could be spillage. There may be stuff at the left side that may also be on the right side. When you put them together, suddenly it becomes the most frequent item and you never realized it. You can't just take the most frequent item here and the most frequent item here and figure out the largest frequency, because there may be something at the end of this range, there may be something at the end of this range that would come together and suddenly become more frequent. Did that make sense? So how am I going to deal with all this? This looks hard suddenly. Should I go back to that picture? So that's my problem. I have a sorted array with repeats. And what I'm trying to do is to find the most frequent item in any given range. So are you still happy with your tree-based solution?
You could also store how many numbers for each node, how many numbers you have on each edge.
Okay.
So then when you're searching for the range,
Uh-huh.
you compare both nodes and also the number in between both nodes.
Okay, so how much more information do I have to store at each node now?
How many numbers you have on the left and on the right?
Well, so remember that here's my subtree. I'm just going to draw it as a triangle, right? Somewhere here is my most frequent item, let's say. So all I have to do is to say this item has frequency whatever. So I say that I have item X with frequency f of X, let's say. What else do I need to store here in order for me to merge this with another tree just on its right with something else that says Y and f of Y? Right? This is what I have to answer, correct?
The current count of the unique value that it is you're looking at?
Yeah, that is exactly, f of X is exactly that. That's the frequency of X. Right? That's the count.
Does it have to be a tree?
Okay, you have other thoughts? Well, we discounted a 2D array. So we don't have 2D arrays. We don't have, if we don't want trees, then we haven't learned anything else in our data structures class, so we don't really know. Well, we know a graph, but that's even more complicated than a tree. So if we can't work with a tree, we're not going to get to a graph. Well, what I want you to do is to think about all the energy you put into understanding the previous problem. Can I bring that to bear here? That's really where I want to take you, not for you to start off and and think afresh, because that may or may not be very productive. Yeah, Usman, you had a thought?
No, I was thinking about how about you keep count of each elements, like count and then make it 3 by using like just a single value 1, 3, 6, 9, 15, 24, 39.
Okay, very good, yeah. And then?
And then from 1 to maybe, okay, and then from 1 to maybe half of like 39. The index it's 1, 3, 6, 9, 15, 34. Half and then store.
So you want to store all the unique items and then do what?
Each.
By the way, he's on the right track.
Okay, so each.
So better pay attention.
Each element you store its frequency on its side.
Okay, very good. So he's storing all the unique items and their frequencies in a new array, right?
Yeah.
Okay. So items and their frequencies. How does that help me? Okay, good. That you're on a roll now. What else? What should I do next?
Yeah, and then just form it into some sort of a tree. So use some sort of banner research.
Okay. He
For
wants to
example-
use a tree after that. Does that make any sense for you? So good. So let me take you from there and see if we could flesh out something that's more meaningful. Yeah. Did everyone understand the basic idea? The basic, yes,
Can you repeat it?
of course. The basic idea is, yeah, there are repeats here. Why bother with repeats? Let's just keep one copy, but we'll keep its frequency. So we'll remember that 1 showed up twice, 3 showed up 4 times, 6 showed up once, 9 showed up 3 times, and so on and so forth. Fine? So now, I don't really care about the actual value, 1, 3, 6, and 9. I care more about the frequencies. So now think about an array of frequencies. Now what am I asking?
Maybe this is going the wrong direction, but perhaps bucket sort. Where
Yeah.
usually-
Let's not go in some other direction. We want to use everything we've learned so far with the other problem over here. And this is something that's good training for you, because just because using stuff we've already built will save you a lot of time and a lot of effort. You want to, any new problem you get, if you can match it to something you've already solved, half your job is done. Okay? If you're going to say, yeah, I'm going to reuse a tree, great. You should be thinking about it. Now, what I'm trying to tell you is that whatever he helped you with in terms of turning it into an array of frequencies is going to help you, because you're trying to find the item with the largest frequency, right? So those frequencies are there, and so it's almost like if I have to search the whole array, all I have to do is to find the largest number, which is the same as our first problem, right? So it should look very much like what we've already solved. That's what I want you to do. So don't get me wrong. I mean, it's possible that some other solution will work, and there are many solutions here. I want you to reuse things that we've already built, and it'll turn out that this is actually quite efficient. It's going to be very hard to beat the solution that will eventually emerge here, but other solutions are of course possible. So right. So this is the problem. We're given an array that is sorted. I don't know if sorted really matters at all here. In fact, they could be. It could simply be that if there are equal items, they're next to each other. That's all we care about. And we want to know what's the most frequent item in any given range. That's what we're interested in. So, what is this picture I have here? Right. This animation is messed up. Sorry about that. So, here's my plan, or here is his plan, Usman's plan. You take the array that we started with, right? we have 1s and 3s and 6. So this is the sorted array with repeats. And then I am, of course, going to give it indices, but I'm also going to build this thing over here, which will start to make sense immediately for you, which says that between 1 and 2, they're all 1s. Between 3 and 4, sorry, what did I do here?
Between 3 and 6.
Yeah,
Yeah, most
yeah,
different.
okay, fine. Oh, I see, sorry. So this is one way to build a tree. I think I may have messed up.
It looks
This
right.
also works, nothing particularly wrong with this. Sorry, you're gonna say something?
I think it looks right. So you have the range
It looks
and
right.
the number and the number of times it appears.
Yeah, yeah. So then I'm building the next level of the tree, but I'm doing something that's, so here I have 1 to 2, that is all 1s. Then I have 3 to 6, that's all 3s, right? And 3 appears 4 times, that's what I've meant by 3, 4, not the range 3, 4, right? Then from 7 to 7 is only 6 and it appears once. Then I have 8 through 10 are 9s and it appears 3 times. I have 11 that appears, 15 that appears once, 24 that appears 3 times, and then 39 that appears once. So I've turned this into all the unique values along with their frequencies. So these are your unique values, 1, 3, 6, 9, 15, 24, and 39, along with their frequencies, which is 2, 4, 1, 3, 1, 3, 1. Fine? So I've turned the original array into a different array, but this time it's an array with unique values and their frequencies. Now imagine taking this and sticking it into our tree. How much time do I have? How am I doing?
5 minutes.
I have 5 minutes, okay. So now imagine taking this and sticking it into a tree. Now I've got 1, 2 here, I have 3, 6 here. This range becomes 1, 6, right? And the most frequent item there is, well, this one only appeared twice, this one appeared 4 times, so therefore the most frequent item is 3, it appears 4 times. I have a similar thing here, this one appears once, this one appears 3 times, so therefore the most frequent item is 9, it appears 3 times. And the range here is 7 through 10, here it's 11 through 13. So the ranges at the next level are not nice like before. They're a little awkward. They get broken up where the numbers change, but they are still meaningful. Okay? So in the end, I get the tree, and it's still possible to show that this tree is log n height because the number of leaves are the number of unique items in the array, and therefore this height is still going to be log n. Now the question is, if I give you a range I, j, how do I find the most frequent item? Again, we're going to break this down into 2 things. What if there's an ij that's already in the tree? Say, for instance, a 1, 10, okay, or 11, 15. If I ask you this, if it's already in the tree, all I do is read out the answer that's already stored there, right? And you know how to find this range, and you know where to locate it. And what if it's not something that's in the tree? So let's say I go from, I don't know, 5 through 12. What's the most frequent item from 5 through 12? Okay, of course 5 through 12 is nowhere in this tree, that's pretty obvious. So what I do is first I locate 5, which will be somewhere here. I locate 12, which will be somewhere here. And then find the right subtree and the left subtree that are hanging just like we did last time. But this time I have to be a little bit careful because because the left end, the location was 5 through 12, 5 falls somewhere in between this range. So its frequency is not 4 now, but it's whatever is left of that range. Since the range is from 3 to 6 and my location is 5, I'm only left with 5 and 6, so its real frequency is only 2. So I have to pass 2 up the tree and be more careful with what I write down. That's all. So with a little extra care and attention, I can take care of any range that falls anywhere, even if it's not quite at either at 3 or 6, or even if it's somewhere in between 3 and 6. Okay? The rest of the ranges are all going to be in their entirety because they all fall in between this given range, right? And 12 will fall here. 12 is not a problem because it just starts 24, so 24 only has frequency 1. So therefore, I may have to go and refigure out some of these maximum, but that can all be very quickly done. Essentially, it still becomes a log n computation, and the whole thing works out with the exact same work we did last time.